Welcome to Game Theory. In this lesson, I'm going to talk about sequential games. There'll be a second part to this lesson where I look at two more complex sequential games. In this lesson, we'll be looking at some simpler games and some of the ideas for solving those. So let's start off with an example that I've showed you much earlier in another lesson at the beginning of this series. And we'll kind of use this to get familiar with this backward induction process. So if you've forgotten the game, and I can understand why you may have, since it was presented quite a few lessons back, the idea was that Aristotle is selling a computer to Bernice, and he has three options. He can sell it for 3,000, or he can offer it for 3,000, 2,000, or 1,000, and Bernice could either decide to accept or reject. And the catch is that Bernice values the computer at 2,500. So if Aristotle offers it at 3,000, he would have a revenue of three. I just put in three rather than 3,000, and Bernice would see a loss of 500, which will right here is minus 0.5. And if she rejects, then neither party loses or gains. In the second option, Bernice would accept because she would see a profit of 0.5 or 500, and Aristotle would see a revenue of 2,000 or 2. And again, in each case, if the offer is rejected, neither party loses or gains. Then in the last case, here, option 1, Aristotle would see a profit of 1, and Bernice would see a profit or a gain of 1.5 or 1,500. And if she rejected, neither party would win or lose. So that's why it's called backward induction. We start at the bottom here. So Aristotle knows the details of the tree and assumes Bernice will select the highest payoff in each of the subtrees. So she'll reject here because minus 0.5 is less than 0. 0 is a bit better payoff. She would accept here because 0.5 is greater than 0. And she would accept here because 1.5 is greater than 0 also. So Aristotle knows that, and he realizes he's not going to get anything here, and he's going to get, even though Bernice will accept here, he could do better by offering 2,000 because he knows Bernice will accept here also. So out of these three possibilities, and assuming that Aristotle knows that Bernice will reject this option number 3, he's going to go with option 2. And so I put that in as a solid arrow. And so this is the solution to the sequential game here using backward induction. That Aristotle would offer at 2,000 and Bernice would accept. So I have some definitions on this slide. The extensive form of a game, and I have an example here, it's basically the game we've been looking at, is a specification of a game that represents the key aspects such as the sequencing of player possible moves, so we see going from top to bottom here, their possible choices at every decision point, and the payoffs for all possible game outcomes. So we have the payoffs here at the bottom, and we've listed Aristotle first and then Bernice second. This whole thing is known as a game tree. And then we have what are called subgames. So that's the subgame. This is another subgame here, and then there's a third subgame. I could draw it in for you. Let's do it in blue. It's getting a little bit crowded, but as you might guess, it's this in here. That's our third subgame. And then the entire tree itself is known as a subgame. The subgames that are not the entire tree are called proper subgames. So we have 3 in our case here. And we have a couple more concepts. A game tree is said to be of finite horizon if the length from the root to node, which is Aristotle in this case, to every leaf is finite. So all our lengths are two links basically. And then one last point, however, it is still possible for a finite horizon game tree to have an infinite number of nodes. And that can happen when a player has an infinite number of possible options at a given decision point, which we don't have here. I have some more definitions here. A game with perfect information is such that at any stage of the game, every player knows exactly what has taken place earlier in the game by all players. It also knows the complete structure and details of the game tree. Otherwise, a game is said to be an imperfect information game. So our example that we've been looking at was the computer is a perfect information game, and that's because, among other things, it's because we assumed Aristotle knew that Beatrice valued the computer at $2,500. If he did not know that, it would be an imperfect information game. In this lesson, we only consider perfect information games. The book by Osborne, and I'll give you the link to this in the information to the video, has detailed coverage of sequential games, including games with perfect and imperfect information. As you might expect, these are more complex to analyze. A subgame, perfect equilibrium, is a refinement of the Nash equilibrium concept that pertains to sequential games, and I covered Nash equilibrium in a previous lesson. A strategy profile is a subgame perfect equilibrium if for every subgame the restriction of the strategy profile to that subgame is a Nash equilibrium of that subgame. So I'll show you an example of this on the next slide. I know this is a little bit hard to take in here. It has been proven that every finite extensive game with perfect information has at least one subgame perfect equilibrium. We saw that in the example we just looked at. There was one equilibrium. Further, the set of subgame perfect equilibria for a finite horizon extensive game with perfect information is equal to the set of strategy profiles determined by backward induction. So again, I'll refer you to Osborne for the proof of these facts here. In this example, I'll illustrate the subgame perfect equilibrium that I talked about on the previous slide. So in the game shown in the figure, player 1 moves first, choosing either A or B. Player 2 observes player 1's choice and then chooses an action at the resulting decision node. The payoffs are shown at the leaves of the tree, with player 1's payoff listed first. So you notice this is not symmetric. If player 1 goes with A, 2 goes with either X or Y. And if player 1 goes with B, player 2 has 3 different choices. Player 2's complete strategy is Y, V. And why is that? Well, if player 1 goes with A, player 2 goes with Y because 3 is bigger than 2. And in this case, player 2 would go with V because 4 is bigger than 3, bigger than 3. So that's why I have these both in darker solid arrow. Given this, player 1 receives a payoff of 2 either from A or B. You notice there's a 2 here and a 2 here. So there's 2 subgame perfect equilibria. A, Y, V, this here, and it also includes this. And the other one is B, Y, V. And again, we include both of the complete strategies for player 2, which seems a little bit odd. It seems to be the standard way of doing things. I took a shot at explaining it a little bit more here, why you add the total strategy for player 2 in both cases. When player 1 chooses A, the right-hand branch is never reached, of course, right, if you go down here. So V does not affect the actual outcome, yet we still have V in the solution here. But V must still be listed because subgame perfection requires player 2's planned action to be optimal even in the subgame that is not reached. Okay, so that's the rule, and you would have the same reasoning for adding Y in the case you're going down this branch here. Okay, so you'll see this if you go in various game theory books, you'll see this type of notation used. Our next example is a variation of something called the ultimatum game, first proposed by Guth. I'll give you the reference to that in the information to this video. The basic idea is that someone, an executor, so we're talking about a will, is to divide a sum of money with another person, the decider, that's the person here. The executor can take either a 50-50 split, that's this branch here, equal, or can make an unequal split of the fortune in his or her favor. For example, 70-30. That's what I actually showed here. Once the executor offers a distribution split, the decider can accept the offer as is or reject. If rejected, the combined payout to the two parties is less than the full amount, for example, 20%. So that's what I did here on the reject. You notice I have 20. I just put a 2 in here, but that was to represent 20%. Further, assume that the executor and decider do not know each other. Their identities will not be revealed to each other, and in general, they have no ability to negotiate during the game or afterwards. So we can do backward induction on this game here. So again, just to emphasize here, on the equal side, it's 50-50. If the decider accepts, they each get 50% of the whatever the money or whatever's in the will. And if the decider rejects, they get a lesser amount, 20% each. I don't know what happens to the other 60%, but they get less than what's in the total amount. Then in the unequal case, the executor offers 70-30, and if the decider accepts, then the decider would get the 30% and the executor would get 70. And if the decider rejects, they would each get a lesser amount, 20%. So if we do the backward analysis on this branch here, going down equal, the decider would accept because 5, and the decider is the second thing here. The decider would accept because 5 is bigger than 2. And in the unequal, even though the executor is kind of being greedy here, the decider would still accept because it's 30 versus 2. So we have 2 accepts on either branch, and the executor looking at this would say, well, if I do equal, I'm going to get 5, but if I do unequal, the decider is still going to accept just following this logic here, and so I'm going to go with unequal. So this is sort of the path. And the perfect subgame is equal, accept, accept. That's using that same notation here. We put the best strategy for the executor here, and then for the decider, we put accept, accept because we want to capture both of these green paths here. Okay, so in the next slide, I'm going to do a variation of this game with probabilities. On this slide, I have 2 variations of the ultimatum game. The main difference is here on the right of the figure. I've changed the payouts here for the decider to be 3 and 3. So the decider doesn't care whether accept or reject, or both ways. the decider gets 3, and so the decider uses a mixed strategy in that case, a probability P for accept and probability 1 minus P for reject. The left-hand side is the same. So if we do a backward analysis here, we see here that the decider would go as accept because 5 is bigger than 2. That was the analysis we had from the last slide, is the same here. Then on this side, the decider would use a mixed strategy because it's 3 and 3. The question is, what would the executor go with in terms of these two? And so the executor would want to have the payoff here, the expected payoff here, bigger than 5. So that would be, the expected payoff would be P times 7, which I have here, plus 2 times 1 minus P, and that's, if you add this up, it's 5P plus 2, and that's greater than or equal to 5 when P is greater than 3/5. So if we let M sub P denote the mixed action in which the decider accepts with P and rejects with 1 minus P, in other words, this strategy here, then for every P greater than or equal to 3/5, less than or equal to 1, the strategy unequal except slash MP is a subgame perfect equilibrium. So whatever you're in this range, the executor would go unequal, and then the two strategies for the decider would be accept on this side, and then the mixed strategy here. If you recall, this is not part of the main flow, but it's using the notation that we discussed on the last slide. We would show both of the optimal strategies for the decider. So the decider chooses accept following an equal offer and uses the mixed strategy M sub P following an unequal offer. And then there's yet another variation that I mentioned here. The cutoff probability depends on how favorable the unequal division is to the executor. If we change from 7-3 to 8-2, and we make this 2-2, so again, the decider has 2 or 2 in either case and doesn't care whether accept or reject. It uses a mixed strategy. The executor's expected payoff from unequal would be now 8P plus 2 times 1 minus P, or 6P plus 2. And the executor would want to compare this to 5. In other words, this value here, 5. And then you just subtract, when is this greater or equal to 5? Well, you subtract 2, and you get 6P greater than or equal to 3, or P greater than or equal to 1/2. So the more favorable unequal division, therefore, lowers the required probability of acceptance, in this case from 3/5 to 1/2. I have one last example in this lesson. Payoffs in a game do not have to equal the amount of money received. Instead, they are numerical representations of how each player values the possible outcomes. So that's what I have here. These are just values of relative to the decider and the executor. In the modified game shown below, the numbers 1 to 4 for the executor and 1 to 3 for the decider represent preference rankings, with larger numbers indicating more preferred outcomes. So for example, the executor down here would favor 4 over 1, and the decider would favor the 3 over the 1. But they don't represent money. They could just represent some other value that they have in relation to this game here. These rankings may reflect not only the amount of money received, but also considerations such as fairness or satisfaction with the outcome. And they may not reflect money at all, actually. Using backward induction, the decider accepts either offer. Let's look at this. If we go down this way here, the decider would pick 3 over 1, so yes, that would be an accept. If we go down this branch here, it would be 2 as opposed to 1. So again, the decider would accept in both cases. So choosing equal therefore gives the executor a payoff of 4 because the executor knows the decider would go with accept. And choosing unequal, the executor would get a payoff of 3. So the executor would go with equal, and then the optimal strategy for the decider in both cases would be accept after equal, again using this unusual notation, and then accept after unequal. So this would be a subgame perfect equilibrium. The critical point in this example is that game theoretic payoffs should reflect the value of the possible outcomes as perceived by the players, rather than necessarily representing the money amounts involved. Okay, so we still have this 50-50, 70-30 distribution, but maybe they're, unlike the first way I presented the example, maybe they do know each other, and maybe there's some preference, to have it turn out fairly, as fair as possible, uh, so that may affect their relative value uh, in terms of the different decisions. Okay, so that was the last slide for this lesson. I have one more lesson on the same topic, sequential games. It's actually 2 games where the analysis is kind of long, and I could have squeezed it into this lesson, but I decided to make one more lesson. And then that'll be the last lesson in this game theory playlist. So if you like this, please remember to give it a thumbs up.